we're going to look at some different interpretations and applications. So more stuff. Some of it will be review. Some of it will be a little bit different of the definite integral. So something to keep in mind, and we talked about this with derivatives, that if you take the derivative, if you have like the temperature outside and you take the derivative, if you have an equation that represents temperature, if you take the derivative of temperature, the temperature function, you get the rate of change of the temperature. So differentiating turns an amount into a rate of change. When you integrate a rate of change, when you integrate a rate, it takes the rate off it and just makes it the amount. It makes it the change in the y value. Remember, a rate is change in y over change in x. So it would be a change in the y value, whatever your y is measuring. So in this case, for example, water is being drained. So you can pause it and read about this water being drained from the swimming pool. Okay, so what would the units of the derivative be? The units would be in cubic feet, right? That's the amount of volume, but then it's a rate, so per hour. So if we took the derivative of that for r prime of t, it would be cubic feet per hour. Okay, so now if we integrate from a to b that rate, we end up with the amount of change on that interval and that during that time period from a to b. So in context of the example above with the draining pool, if I integrate the rate at which the water is changing, I'll get the R of B, capital R of B minus capital R of A. That means that would represent the amount of water that has drained from the pool between t equals A and t equals B hours. You could also think of it as the change in how much the water has changed. It's not how much water is in there, but how much the water has changed in the pool, the net change. So if we use this table given below, it represents the velocity of a particle at different times t. We want to approximate the value of the integral from 0 to 30 of v of t. Using the midpoint Riemann sum, we're going to use using correct units of measure, explain what this value represents. So let's do 1, 2, 3 subintervals here. And those are all midpoints there. So the integral from 0 to 30 of v sub t dt can be approximated by the sum of the areas of the rectangles. Now each rectangle has a width of 10, so we could factor that out. And then we do the height of the midpoints, which are these three values. So we've got 1.6 plus 3.1 plus 1.6 again. And that's going to work out to 63 feet. Now remember, the units is feet, okay? Because now we're integrating velocity, which is a rate, feet per minute. We kind of lose the minutes. We're just doing the feet. We're just doing the change in y. All right, v of t is change in feet over change in minutes, right? That's feet per minute. So when we integrate, we're just sort of, this kind of change in minutes is coming to the other side, and we're integrating, and we're just getting the change in feet, essentially. So 63 feet is not how much water is in the pool. I cannot stress that. Or, sorry, this is a velocity one. 63 feet is not the position. It's what the change of position over that time period from 0 to 30 was. We don't know what the position was to start. Okay, so we use the correct units of measure. Explain what this value represents. So the integral represents the total change in distance. That's the key there. It's not what the distance is. From time 0 to time 30 minutes. Okay, what is the value of and using correct. So this one we're going to do the value from 5 to 25 of a of t. We can find the exact value because the integral or the antiderivative of a of t is velocity of t. And so it's v of 25 minus v of 5. We can pull that information off the table. 1.6 minus 1.6. So that's going to be 0 feet per minute. Okay, so when we integrate acceleration, we're integrating a rate of change of a rate of change. It just becomes the rate of change. So 0 feet per minute. What this represents is not the velocity at any given time. It represents the amount of change or the net change from 5 doesn't mean the velocity is 0. It just means the velocity at 25 is what it was at 5. There was no net change. All right, let's look at the next one. This table represents the temperature of water in a tub at time t. So I'm not going to read to you. You can read it. Using the data in the table, estimate the value of W prime of 12. Using correct units, interpret the meaning of this. So we have W here in our y value. So the W prime of t, of 12. We want to approximate the derivative using the secant line here. So we'll use our approximation. And 12 falls between 9 and 15. So it's going to be W of 9 minus W of 15 all over 9 minus 15, which is about 61.8, 67.9 over negative 6. That works out to be 1.017 degrees Fahrenheit. Now this is a rate, so because it's a derivative of an amount in degrees, so now it's per whatever the time units were, minute. Okay, so that's per minute. So what does this mean? At t equals 12 minutes, the temperature of the water in the tub is increasing at a rate of 1.017 degrees Fahrenheit per minute. You could just say is changing at a rate. You don't need to add the increasing. So the next one, use the data to evaluate from 0 to 20 W prime of t dt. Using correct units, interpret the meaning of the integral of this problem. So the integral, we don't have to estimate, right? We can find the exact one because when we integrate W prime, we get W, and we can pull that information right off the table. And now we're integrating the rate, so we're back to just degrees Fahrenheit. And what does that mean? Or what does that represent? It represents, remember when we do this integral, the amount that temperature has changed from t equals 0 to t equals 20 minutes. So in this case, the temperature rose. For 20 to 25, the function w that models the water temperature has a first derivative given by the function. So now they're giving us the derivative, the equation or the function. Based on that model, what is the temperature of the water at time t equals 25? So if I go back to here, there's no 25 on the table. So how the heck am I going to do this one? Here's where we can use the fundamental theorem of calculus. we have an equation for W prime, and we want an equation for W. That means we can integrate W prime to get W. So if I go from 20 to 25 of 0.4 square root of t cosine of 0.06 t dt, that's going to be equal to W of 25 minus W of 20. So why did I, oh no, 20 was on the thing. So what we can do here is we're going to use our calculator to evaluate that integral. So you can pause your calculator and do fn int. You should get that number. And then we want to find out what W of 25 is. We know that 20 is 71 degrees based on the table. So I can add 71 to both sides. So we get 73.043 degrees Fahrenheit. Keep in mind, an alternate way to think about this is that integral represents the change, the net change, and we're going from 20 to 25. So if we know that 20 is 71, so it's like 71 plus the integral of the change. So here's where we know our initial amount, or our amount at 20. That's like our starting amount. It's already 71 degrees. The integral here, I'm not going to recopy this whole function. I'll just say W prime of t. That integral, this would represent the change. So again, I kind of think of money. If you had $71 in your bank account and I said that it changed, it went up by $2, then you would now have $73 in your bank account. Just finding the integral is not enough. So that's another way to think about this, where you don't have to do the fundamental theorem of calculus and solve for the W of 25. If you kind of understand this as an accumulation, that's an accumulation. That's how much temperature you've accumulated, and it could be positive or negative. In this case, it's a positive change. So we add that to where we started at time 20. So it's another way to think about that one. Okay, so let's look at the next one. This one is about temperature of biscuits that are baking. So a pan of biscuits is removed, so they're done baking. Pull them out, and they're going to start cooling off. At 0 minutes, the temperature is 100 degrees Celsius, so they're sort of telling us, I should say B of 0 equals 100. That's sort of what they're telling us there. The rate at which the temperature of the biscuits is changing is modeled by the function there. So that's a derivative function, right? So I don't have B of t yet, but I can figure out some stuff from that. So find the value of B prime of 3. So first of all, B prime of 3 is negative 13.84 e to the negative 0.173 times 3. And that's going to be equal to negative 8.236 degrees Celsius per minute. Remember, that's a rate because it's a derivative. Interpret and correct, explain the meaning of this. So this means that 3 minutes after the biscuits are removed, it's an N, the temperature is changing. I'll say this. You should probably just say changing all the time, but I'll say is decreasing at a rate of 8.236 degrees Celsius per minute. I don't want to say it's decreasing at a negative rate, because that means it would actually be increasing. So that's why if we always just say the temperature is changing at a rate of, and you just put the sign of your answer, you'll always be right. You could say increasing when it's positive and nothing, you don't have to worry about anything, but when it's negative, that's the trick there. If you're going to say decreasing, then you got to take the negative off of it. All right, sketch the graph of B prime on the axes below. Explain the context of the problem, why the graph makes sense. So this would be a calculator thing. If you look at your calculator, it's essentially going to do something like this. Okay, so that's the graph of the derivative, remember, not the temperature, but the rate of change of the temperature. Explain the context of the problem, why the graph makes sense. So that means that, let's see, B prime of t represents the rate of change of the temperature of the biscuits. The biscuits are always getting cooler, so that means the rate of change, if the temperature is decreasing, the rate of change must be negative. So that's why the entire curve is below the x-axis. So we could say something about that. Since B of t is always decreasing, B prime of t must always be negative. We could also talk about the rate at which the temperature is decreasing. When you first pull them out of the oven, you're going to have higher rates of change, and then it's going to slow down as we keep going. It's going to cool down a lot in that first minute compared to, say, the 10th minute. It's not going to cool down as much. So the rate of change is slowing down. But this is good enough. We kind of explained why the graph makes sense since we're saying it's below. That would be fine. That's a good enough explanation there. At time t equals 10, what's the temperature of the biscuits? Show your work. So here's the one where I'm going to do this one a different way. So we know at time 0 it's 100. So if we start with our temperature of 100, and then we add the change from that time, which was 0, up until the time they're asking for, which is 10, of our function, negative 13.84 e to the negative 0.173 t dt. That's going to be equal to 100. Let me write it underneath for room. So that's 100, our starting temperature there when we pull them out of the oven. Plus, we do this on our calculator. We're going to get negative 65.817. So then, I should say it this way, B of 10 is equal to that. The temperature after 10 minutes is equal to, that's going to be what, 34.183 degrees Celsius. Okay, we don't have to explain this one in context of the problem. That's nice. Is this our last one? Yes, it is. Very good. Let's see if we can do an under 30-minute video. All right, so you can pause the video and read the question. All right, so welcome back. Let's see, they want us to find that value. So the integral from 10 to 15 of s prime of t, which is, we have the equation 2 sine of 0.03 t plus 1.5 dt. We do that on our calculator, fn int, and we get that number. Now, what is it? This was a rate, and it was measured in what? They measured height in millimeters, and time was in what, days? So, but that was a rate. We now integrate a rate to just get an amount. So it's going to be the y. It's the change in y. Remember, when we integrate a rate, we just get that numerator of the rate, which is change in y, which is y minus y. And the y value in this case, time was our x, our y was millimeters. So then we want to explain what this means. So this represents the amount of change, you could say increase, but be careful when it decreases. The amount of change, I'll just say, in the height of the water over that time period in the can from t equals 10 to t equals 15 days. At the end of the 60-day period, what is the volume of water that had accumulated in the can? Show your work. So this one, we want to know the volume of water. So first we need the height of the water. So this one is a little bit of extra work here. We got volume equals pi r squared h. We know that the radius of the can was what, 10 millimeters? We just need to find what's the h. So that's where we can use, excuse me, we can use integration here, our accumulation function. So remember, I'm given a derivative equation, and if I want to find like an original value, we can use the fundamental theorem of calculus and solve, but now I've just started recently kind of changing over to our starting amount, so they must give us one. During the first 5 days, 3 millimeters have been collected. So we know that 3 is where we're going to start. I'll put a little, we're starting with 3, and that was from, that 5 days had already occurred. So that was from day 5 to day 60. We can integrate this thing. I'm not going to write the whole function again. I'll write s prime of t because you already have it in y1 now. And so that's going to be 3 plus 163.565. So 3 was the amount of water already in the can at time 5. Remember, the integral represents the amount of change that's taken place from day 5 to day 60. So then when we add that, we get our total amount at day 60. So that's the height of water in the can at day 60. So then we plug that number in. I need bigger parentheses here. 166.565. We do that out. We get 52,327.9 millimeters cubed. That's the volume. Okay, last one. The rate at which people enter an auditorium for a concert is modeled by the function given by R of t, blah, blah, blah. R of t is measured in people per hour. I'm not going to read to you. You can pause it and read. Okay, so they are giving us a rate here. So that is like a derivative. Even though it doesn't say R prime, it is a rate. It's measured in people per hour. If they say all the people stayed for the start of the concert, how many people are in the auditorium when the concert begins? So let's see. They're setting up for 2 hours. So they want to know how many people are there when the concert begins. So that means they want to find whatever the antiderivative of R is. We don't have notation because if it were R prime, I'd call it R, but and it's already a capital R. So whatever the primitive function is, that means like the antiderivative. Some function whose derivative is R. I want to find how many people are there when I plug in 2 to that. So what we're going to do is, excuse me, there's 100 people to start. So that's like our initial amount. And then plus our rate. That's at time 0. So now from 0 to the next 2 hours before the concert begins. This is the amount of change in people that will be there. So we can do that integral on our calculator and do 100 plus that, and that will be 1,080 people. Remember now, oh, pencil just died. Remember that we integrated a rate, so now we just have people. We don't have people per hour. So we get rid of the per hour part. So that's 1,080 people. And that's it, yes.